All right, so work and energy relate to one another, and we're going to study that for the next week. Now, everybody has a definition of work. Usually it has some negative connotation. All right? In physics, we have a different definition of work, which I just mentioned. The most basic wordy definition of work is it's a force over a distance, which is what I just said. Or in other words, force times distance. We're going to quantify that a little bit more in just a bit. Right? But I'm going to tell you right now that for all intents and purposes, work is a type of energy. You should think of it as a type of energy. And indeed, if you look at the units, right, so the units of work, which I'll write as W, do not confuse with weight. All right, well, it's a force times a distance, which means it's a Newton times a meter, or a kilogram meter per second squared times a meter. Whoa, what am I doing? Kilogram meter per second squared. Second squared times a meter. All right, or a kilogram meter squared per second squared. Or, you know that, well, what are the units of a Newton meter? Does anybody know the units of a Newton meter? What it's actually called, or the units of energy? A joule. We call this a joule. Capital J for joule. All right, so work, in fact, does have the units of energy. So it basically is energy. And but it relates to specific types of energy in a certain way, and that's what we're really going to be studying and analyzing for the next week. Now, before we do that, let's just talk about different types of energy, just to sort of clear the air. What types of energy might we deal with in a physical system? There's lots of different types. Yeah. Right, so kinetic energy is something that we'll deal with very, very soon here. Kinetic. What? Potential. Yep, we will deal with that. So kinetic energy, just to attach a word to it, is the energy of motion. Potential energy is another type that we'll deal with before too long, which is basically the ability of an object to store energy, or I guess just stored energy somehow. What's that? Torsion? Torsion is sort of more, I would think of as a rotational force. Maybe. Yeah, I wouldn't think of that as energy. If I think what you're talking about, like torsion, like twisting something like that, what you're thinking about is elastic potential energy. So we'll quantify potential. There's different types of potential energy. One of them is elastic potential energy, which could be the energy stored by spinning something up, or just simply in a spring. Right? Other types of potential energy, we have gravitational. Maybe what Rosie was thinking?
Yeah.
Gravitational.
Would that be potential energy?
You could consider it energy. You could consider it to be a potential energy because it's sort of stored inside things. Usually in physics, we sort of just write that down separately because now we say, go talk to chemists. But certainly there's energy stored in chemical bonds, things like that. Right? Another type of energy that we sort of don't consider energy is heat. A lot of the times people don't think of heat as being energy, but it is just that. Right? So we're gonna deal with these. Are just a few examples. We're gonna deal with a few of these. We're certainly, physicists deal with heat. We're not gonna do that in this class. You have to take thermodynamics. We will deal with gravitational potential energy. We'll deal with elastic potential energy. We'll deal with kinetic energy. You'll deal with a different type of potential energy in Physics 224, namely electric potential energy. Okay, so we'll see a few of these. All right, but let's sort of introduce ourselves to the concept of work through a few different through a sort of general example. So imagine that somebody pulls something in a wagon. So kind of do this step by step. I don't know who's gonna. We're gonna go with Ben. My son's name is Ben. So Ben pulls a cow, which doesn't really make sense. He's a tough 4-year-old. All right, in his wagon. And the mass of the cow, 650 kilos. Let me draw a picture of a cow in a wagon. You know this is going to be great. Look, it's a cat. That would make more sense. And Ben is pulling the cow. Something like that. All right, ugly picture, whatever. He pulls with a force of 200 newtons. So he's applying a force. I'm just going to draw it sort of on the cow. 200 newtons to get that cow to move. So I'm going to ask this question. I'm going to ask after. We're going to use all sorts of colors today. After pulling for 10 meters, I want to know how fast is the wagon moving? So if you're applying a force to a cow, what is going to happen to that cow? It's going to accelerate. So maybe we could solve for an acceleration. Now that doesn't give us the speed. What can we do with the acceleration? Use kinematics. All right, so we can do what you've done recently. You can use dynamics. You can use Newton's second law to solve for the acceleration, and you can use kinematics to solve for the speed. So we could do that. We can do it pretty quickly because there's only one force that we care about here. The acceleration is just the force due to Ben divided by the mass of the cow, which is 200 newtons divided by, what did I say, 650 kilograms. So it's something like 0.31 meters per second. So my 4-year-old son can accelerate a cow at 0.3 meters per second squared. Fantastic. I'll have to tell him that. He'll be very proud. And then we can go back and we can use some kinematics to solve for the final speed. So if I use that old v squared equals v naught squared plus 2a delta x, you solve that, you should get v is equal to 2.4 meters per second. Fantastic. Well, that's fine, but what happens if we change this problem just a little bit? So let's say now instead of the cow, Ben pulls his dad. I guess that's me. All right. Well, dad weighs less than the cow. It's getting closer every day. All right. We'll just make it a nice round 100 kilograms, which might be a little bit on the large side, but that's okay. So again, the acceleration is equal to force that Ben's pulling at, still 200 newtons, the mass of dad, which is now 100 newtons. So you get the acceleration is equal to 2 meters per second squared. Right? So now, of course, since there's less inertia, the wagon and the object in the wagon accelerate at a higher rate, at a greater rate. Again, we apply the same equation, v squared is equal to v naught squared plus 2a delta x to get the final velocity, and the final velocity is 6.3 meters per second. Right, so if it's accelerating at a faster rate over the same distance, you get a larger final velocity. Just to keep going here, instead of dad, now Ben pulls a flower. All right, well, certainly the flower weighs quite a bit less. Mass of the flower is something like, what did I say, 0.5 kilograms? 20 kilograms. Doesn't really matter. He pulls a lot of flowers. Very, very massive flower. It's the biggest sunflower ever. All right, so the acceleration F over m, really cruising now, so you get 10 meters per second squared, which is a very large acceleration. And so if you solve for the final velocity, you get something like 14 meters per second, all right, after the 10 meters that he's pulled the thing. All right, so where am I going with this? So what I want to look at then is sort of in number terms what we've already kind of talked about. What we're seeing here is that he's pulling with the same force each time, but the final velocity is changing. So we had the cow, dad, flowers. They each had a different mass, 650 kilograms. Dad was 100. The flower was 20. An acceleration of 0.3 meters per second squared, 2 and 10, and that resulted in different velocities, 2.4 meters per second, 6.3, and 14. All right, so all those quantities are different. The question then becomes, well, is there some quantity that isn't different? I don't know. I guess if we multiply different combinations of these things, we might discover that for the cow, if we did something like mass times speed squared, so 650 times 2.4 squared, I think gives us something like 4,000, right? And this is a kilogram meter per second squared, meter squared per second squared. Right? If you did 100 times 6.3 squared, I think you'd get about 4,000. And if you did 20 times 14 squared, you should get about 4,000. So this quantity, mv squared, is constant from object to object, which sort of seems like it might be okay because we're applying the same force in each case over the same distance. So that's sort of nice. Now, of course, we've already seen that this is a joule, so this is somehow related to energy. And if you know anything about kinetic energy, this equation looks very similar to kinetic energy, something that we're gonna talk about in some detail. Okay? Now, as it turns out, you can arrive at this in a slightly different manner. For each object, Ben was applying a force of 200 newtons, that's an ugly N, over a distance of 10 meters. Each object is exactly the same. So that's a force over a distance, which we just said is work. So the work in each case was something like 2,000 joules. So in each case, the work was the same. In each case, this quantity, mv squared, was the same. So the question is, how does this relate to that? Well, clearly there's a factor of 1/2. So we can say that in this case, the work done by Ben is equal to 1/2 times the quantity mv squared. And that holds for each object. So if I change the mass of the object, but I apply the same amount of work, what happens to the speed? It goes up. It must go up. So this is, in essence, the concept behind the work-energy theorem. So what we're really getting at here is this thing called the work-energy theorem. Work-energy theorem is pretty important stuff, and it's not terribly obvious. All right? The work-energy theorem says that if you do some work on an object, that will cause a change in velocity. All right? Now, in this equation here, we have something like 1/2 mv squared, but really what we're missing here is that cow or the dad or the flower, they all started from rest. So they started from a speed of 0, and then at the end of the process, they had a speed of whatever their speed was. So really, we're talking about a difference. We're not talking about just some random value 1/2 mv squared. We're talking about a difference between some final 1/2 mv squared and some initial 1/2 mv squared. All right? And if you've been reading ahead or if you've taken physics before, you know that 1/2 mv squared is actually referred to as kinetic energy. So the work-energy theorem says that, says that the change in kinetic energy of some object is equal to the work done, must be equal to the work done on that object. Okay? This theorem, this equation, tends to be much easier to solve than what we did. In order to get the final velocity, the final speed of the cow or the dad or the flower, we had to solve for the acceleration using a free body diagram. We applied Newton's second law. We got the equation, or we got an acceleration. Then we went back and applied kinematics. Well, now you can see that, well, I know work is just force over a distance. All right? I know, 1/2 mv squared. This is not hard to solve. The final velocity is what I was after, the mass I was given. The initial velocity was 0 in our example. So instead of having to solve 2 or 3 equations, which I did initially, I could have solved that whole problem with a single equation. So it tends to be a bit simpler. The other reason it's simpler is because you'll notice an absence of any vector signs here. In other words, energy is a scalar. So you don't have to solve any vector equations. Energy is a scalar. You don't care about the direction of the speed or the direction of the velocity. It's just going to be, you just care about the speed of the object, the magnitude of the velocity. All right? This equation should be, this theorem, this equation should be actually reasonably obvious if you really think about it. So let's look at, let's look at an example. We'll rearrange the terms. So let's look at, all right, the final kinetic energy of some system. We'll do like a car. So imagine that you want to find the final speed of some object, which is what we just did. Well, that's equal to the initial kinetic energy, the initial, or something to do with the initial speed, plus the work. That's all that equation says. So imagine we have like a car then. So you've got a car that starts off going really fast. Right? Well, and then you put on the brakes. So you apply a force due to the brakes, which is like a frictional force. In other words, the brakes do work on the car. So what happens at a later time after you've applied the brakes for a little while? Well, you're moving slower. Right? There's nothing really complicated here, but that's exactly what our equation says. Right? So here we have a large KE. We apply brakes, so the brakes do work. And then we have a small kinetic energy. Now, this simple example sort of illustrates something, though. All right? Energy can be added to a system. Energy can be taken away from a system. In this case, brakes are doing work on the system, but what are they doing? They're taking away energy. Initially, we had a lot of energy. We had a lot of kinetic energy. Later on, we had a little kinetic energy. In order to go from a lot to a little, then something had to take the energy away. So the brakes took the energy away. So in this case, what we would say is that the work done by the brakes has got to be negative because they're taking energy away from the system. The way that we can see that graphically is when we have a force that is directed opposite to the displacement. So this is the displacement vector. This is the force vector. Then the work is negative. In this case, the displacement, this car initially has a velocity to the right. Later on, it has a velocity to the right, so the displacement was to the right. The force was to the left. So the brakes did negative work on the system. All right? Energy is a scalar, but it can be added or subtracted. So a negative sign does make a difference. So you keep that in mind. Right? We're going to come back and see another way to determine the sign of, or another way that makes it obvious what the sign of work is in just a little bit. But before we do that, let's do another example. All right, so we'll go with the text tool. To the text tool. But first, the spinning wheel of death. All right, so. Nope, 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 nope. What's happening? What's happening? Thank you. All right, so we've got somebody jumping off the side of a roof. So a gentleman by the name of Barney jumps off the roof of a building. Somebody standing by says that he moves by at 30 meters per second. So somebody makes an observation of the speed of Barney as he flies past them, standing at a window. A few seconds later, Barney passes somebody else, and that person observes there he goes at 50 meters per second. All right, so this, just to stick a picture on this, we have a roof, we have a jumper, and the jumper is observed at 2 spots. So this is, we're showing 2 instances of 2 snapshots. There's one person and there's the other person. All right, so right here, Barney's moving at 30 meters per second. A little bit later, Barney's moving at 50 meters per second. All right, so the question that I'm asking here is how much higher is Lily's office? Than Ted's. All right, so this is absolutely 100%. You can use Newton's second law. Actually, you can use kinematics to solve this problem. All right, but we could also apply the work energy theorem here. So in order to apply the work energy theorem, though, you have to have a force doing work, right? So what force is doing work in this problem? Gravity. It's the only force in the problem, so it's a pretty good bet. So gravity is doing the work in this problem. Tell me about the sign of the work. Is it positive or is it negative? I'm sorry? Well, so what's the, yeah, so you're asking the right question. What is the displacement? What is Barney's displacement? So he goes from here to here, and it's downwards. The force due to gravity is certainly downwards. Rumble. All right, so F sub g is downwards, so work must be positive. All right, that's good to know. All right, so we'll apply the work energy theorem, and I'm going to write it, it doesn't really matter, we'll write it this way. Kinetic energy final is equal to kinetic energy initial plus work. Right? Well, we just plug in our different quantities. So we know that the final kinetic energy is equal to 1/2 mv final squared. The initial energy is 1/2 mv initial squared. And the work is just some force times the distance. That's what we said work is, force times the distance, at least for now. All right, well, I'm after the distance between the two offices, so I can solve, I mean, it's just work from here to here. That's the work is being applied over that interval, so I can solve for distance. That's going to be equal to 1/2 mv final squared minus 1/2 mv initial squared, all divided by d. I'm sorry, all divided by f. In this case, the force due to gravity. All right, so you have an equation. It's not too bad because we know everything. We know the mass, or at least we know that the mass doesn't matter in this problem because F sub g is just mass times gravity. So the masses divide out. So I'm just solving 1/2 times the final velocity squared is 50 meters per second. minus 1/2 times the initial velocity squared, 30 meters per second, divided by gravity, which is just 9.8 meters per second squared. All right, so you can solve that pretty easily. You should get a difference of 12.2 meters, I think, I hope. Seems about right. Okay, so we used a single equation to solve for the distance between the two opposites. So we're not really doing anything new here. I mean, we could have solved this problem using Newton's second law and then kinematics. Nothing new. But we were able to save ourselves a little bit of effort by applying the work energy theorem. Okay, so that's something to keep in mind. All right. Now we're going to add a few complications. All right, so complication number 1. All right, the first complication. Work is not just force times distance. Unfortunately, it's not quite so simple. But that's not too big a deal. And we're going to try to illustrate that using the old inclined plane problem. All right, so in the inclined plane problem, we had a box sitting on a ramp. And that box is going to slide down the plane. All right, we've got a few forces here. Actually, let me draw straight that. So we've got some displacement down the plane. Now gravity is pulling this object straight down. All right? And you could certainly make the case that gravity is the thing that's doing work, right? Because if there was no gravity, it wouldn't slide. So gravity is the force that's doing work on this box. There's a normal force, but the normal force isn't really making it slide down the ramp because the normal force is perpendicular to the displacement. So it's not quite so simple, though, as work being equal to force times distance. Because, if you said, well, if the normal force isn't contributing any work, the normal force isn't causing motion because it's perpendicular. Well, if gravity were somehow perpendicular, then it couldn't do any work either. So we have to be able to account for the fact that a force that's perpendicular to a distance, a displacement, doesn't do any work. Work is a scalar. But somehow direction has to matter. So we can write down an equation for that. If we account for the fact that the force is a vector, the displacement is a vector, and we throw in a dot. So if you remember now back to chapter 1, we did that thing called the dot product. And you'll remember that the dot product operation results in a scalar. So when you take a vector and you dot it with another vector, what you get out is a scalar, which is great because, well, like we talked about, energy and work are scalars. But this at least gives us a way to take into account the fact that the force and the displacement are in fact vectors. Now, if you remember, there was another way to write down the dot product in terms of the magnitudes of the force. Do you remember this? So the magnitude of the force times the magnitude of the displacement times something else. All right, good. So I can write down any dot product this way, all right, or I can write it down using magnitudes times the cosine of the angle between, which I'll just call theta. All right, in this example here, I have gravity pointing downwards, displacement is off here, so this is theta, right? So the angle between the two. All right. Well, let's say instead of calculating the work done by gravity, we're interested in this problem on the work done by the normal force, which I already said is 0. Does this equation bear that? Well, the normal force is perpendicular. So in this specific example, what I'm saying is the normal force times the magnitude of the displacement times the cosine of theta. These two are perpendicular. So theta is 90 degrees. The cosine of 90 degrees is 0. So yes, in fact, the work done by the normal force, say the work done by the normal force, is equal to 0. And the work done by gravity, since the angle between gravity and the displacement vector is certainly not 90 degrees, the work done by gravity is non-zero. Right? So that will, the fact that we use the dot product allows us to capture those things. Okay, now to take that a step further, in our car example, where we had a displacement to the right, but a force to the left, the force due to the brakes to the left, I told you that the work done by the brakes was negative. Does that make sense? So the work done by the brakes in that example is equal to the force due to the brakes times d, the magnitude of d, times cosine of theta. In this case, theta is this angle. They're anti-parallel. So theta is 180 degrees. The cosine of 180 degrees is negative 1. Right? So the work done by the brakes is negative times the force due to the brakes, which has got to be a positive number because it's a magnitude, times the displacement, also positive. All right, so the work done by the brakes is definitely negative. All right, so the use of the dot product allows us to capture all these sign conventions without having while still allowing work to be a vector, as a scalar, as it should be. So we're happy about that. All right, so complication number 2. All right. The second complication is what if the force varies? So I'm drawing some sort of a van. And imagine in this example you are trying to push this guy to get it moving. And you're applying some force of 500 newtons. All right. Well, as you probably know, if you're trying to push a van, that once you get that van moving a bit, you tend to have to push a little bit harder to keep it moving. Why? Because you get tired. In other words, as you push and push and push, you exert less and less force. Because it's a lot of work pushing a van. It's really hard for me to draw 3 vans in a row that all look the same. All right, so here we have a van and we're pushing with 80 newtons and we're about to pass out. Well, so if I want to figure out the work, if I want to figure out so let's say the van started from rest, I want to find the final speed of the van. All right, so just the same problem we've been doing, with the additional complication that, I'm pushing with a different force each time. So how would you do that? Well, I guess one way you could do that is you'd say, well, I'll figure out the work done by my first segment. I'll add that to the work done by my second segment. Now I'll add the two of them to the work done by the third segment. So the work total would be something like work 1 plus work 2 plus work 3. That's fine, and that gets you the right answer. But the problem is, that's sort of making the assumption that, well, I'm pushing for some fixed amount of time. So really, I'm pushing with a constant force, then just a different constant force, and then finally a third constant force. And that's fine. So I get the sum of the force I times displacement I. If I write this down in a nice mathematical, consistent way, if I sum up all the different components of the force over the respective displacements, I can get the work. Right? That's great, but in this example, I'm probably thinking that I'm not just going from 500 newtons to 200 newtons, and then a few seconds later, I'm dropping down to 80 newtons. What happens if I'm going from 500 to 200 newtons nice and smooth like? What changes things? Mathematically, how can I represent that? Take the integral. Exactly. So really, this becomes an integration problem. So the total work done, all right, is equal to the integral of the force, which is a function of the displacement, right, dot dx, where dx is a vector. Dx is a vector that represents that has the direction of the displacement. Right? And I'm integrating over this. I'm integrating this from some initial, I guess I should say initial position, so maybe d I to d final.